Sketch and analyze the graph of each function. Describe its domain, range, intercepts, asymptotes, and behavior, and where the function is increasing or decreasing. So we have an exponential function, 3 to the x, and we can plug in some points, some x values, -3, -2, -1, 0, 1, 2, and 3. Not all of these will fit, but that's kind of the standard -3 to 3 on most graphs. So -3, 3 to the -3 is like 1 over 3 to the third, because that negative power sends the value down to the denominator. We have 1/27. Then this will be 1/9, that'll be 1/3, and anything to the 0 power is 1, except for 0. So 0, 1, 1, or -1 is a third, and then a 9th, and then a 27th. It's even hard to graph because the values just get so small so quickly. So we kind of do that action right there. And then with 1, it's 3, 9, and then 27. So 1, 2, 3, 4, 5, 6, 7, 8, 9. If I go by ones, I'm off the map pretty quickly. So exponential growth increases very, very quickly. Now, if we're going to answer all the questions, here we go. We got describe its domain, -infinity to infinity. There's no radicals. There could be a variable in the denominator, but even if the variable's in the denominator, 1 over 3 to the -1, you can't make the denominator 0. That's impossible. The range is 0 to infinity. We have a y-intercept at 0, 1 for this one. The asymptotes, this will level out to 0, but it'll never get to 0. So there's an asymptote at y equals 0. The end behavior, well, there's two different behaviors. On the right side, the limit as x approaches infinity of f of x, that's shooting up to infinity. But the limit as x approaches -infinity of f of x equals not at -infinity, but 0 rather. And where the function is increasing or decreasing, so increasing from -infinity to infinity. We always describe increasing and decreasing as going from left to right. So this function increases the entire time. Any questions on that? Well, if the general form of an exponential looks like that, I mean, you know what a parabola looks like. You know what absolute value looks like. You know what square root looks like, most of you, hopefully. So you have all these general graphs in mind. Hopefully, we're putting in the exponential. So like this could be 2 to the x, or 3 to the x, or 4 to the x. That's what the shape it's going to take. Well, now if 2 to the x looks like this, then 2 to the -x, that's a negative on the inside. So that reflects over the y-axis. So now 2 to the -x looks like this if we reflect over the y-axis. Now if you want, you could plug in values. X, y, -3, -2, -1, 0, 1, 2, and 3. But you're going to see in the end, it just reflects over the y-axis. Because 2 to the -3 is 2 to the -3. That is going to be, that's where you get the 8, the 4, the 2, the 1. And then when you plug 1 in, you get 2 to the -1. That's a half. So here's where you get a half, a fourth, and an eighth. Well, now the negatives are giving you the integers, and the positives are giving you the fractions. So when we plug this in, we get 1, 2, 3, 4, 5, 6, 7, 8 here. We get the 1, 2, 3, 4. We get the 2, the 1, the 1/2, the 1/4, the 1/8. So there's that reflecting 2 to the x over the y-axis because the negative is on the inside. So the domain, -infinity to infinity. The range is 0 to infinity again. A lot of this doesn't change. The y-intercept is 0, 1 again. Asymptotes, y equals 0. End behavior, limit as x approaches infinity of f of x is 0. And the limit as x approaches -infinity of f of x, that's shooting off to infinity as we go to the left. And then on this one, decreasing on the entire domain, decreasing -infinity to infinity. What about these transformations? Well, let's get 2 to the x on here. Here's 2 to the x, 2, 3, 4, 5, 6, 7, 8, half, a fourth, an eighth. So here is the parent function, we call this. And then a, b, and c are the children. But this plus 1, this is on the inside of the function, so we'll move everything to the left. So we have left 1, left 1, left 1, left 1. This will be left, left, and left. So this is 2 to the x, move to the left 1. We kind of already have done this. The 2 to the negative x, that's a reflection over the y-axis. So we go back to the blue. There's a reflection over the y, half, fourth, eighth, and then that'll be the 2. Here's the 4, and here's the 8 on the other side of the y-axis right there. Because that negative is on the inside. Then on this last one, we're going to take the blue, we're going to reflect over the x-axis, because that negative is on the outside, reflect over the x, and then we're going to stretch it vertically by a factor of 3. So we'll take the blue and reflect over the x-axis. That's down here, here, that's the 2, 1, 2, 3, 4, 5, 6, 7, 8 right there. There's the half, the fourth, and the eighth. So that's reflect over the x-axis, that's the negative on the outside. And now we got to stretch these vertically by a factor of 3, which means the 1 becomes the 3, 2 becomes 3, 4, 5, 6, and the negative 4 becomes 12. So that's down a little off the map. Negative 1/2 times 3 is negative 3/2. That's here. And then it's kind of this shape right here. Like that. On a side note, in the homework, we have 10 to the negative x plus 3. And this one's always a confusing one because we just don't work with it very much. This is reflect over the y-axis and right 3. And I've told you, remember I told you, on the inside, always go opposite. How come you're not going opposite? Well, you don't get the correct information unless x is positive. We need to factor out the negative, and then when we factor out the negative, if x is negative on the inside, then we get the proper information. So this negative here is reflect over the y, and now that's on the inside. We'll go opposite, so we will go right 3. So you don't have the right information unless x is positive, not negative. With x being negative, your information's all messed up. Compound interest formula. Boy, does that look like a fancy formula, doesn't it? Looks really impressive. I want to take the mystery out of this formula, if you give me just a couple minutes here. This is amount in the bank equals principal times 1 plus the rate over the n raised to the n times t. Wow, fancy. It's not fancy. Principal's 5. Let's say the principal's 500. And let's say the annual percentage rate is 8%. And we're going to compound 4 times. So we're going to compound this quarterly, which means you get interest 4 times a year. But the annual interest rate is 8%. So you don't get 8% every quarter because that's spread out. Can we give the bottle a break? Thank you, appreciate it. You don't get the 8% 4 times. You only get it throughout the entire year. So if I'm going to give you 8% over the year, what percent should I give you in those quarters? 2%, right? 8 divided by 4 times. You should get 2%. So I'll multiply this times 1.02 because we're going to take 8 and divide it by 4. We're going to get 2%. Now why 1? Why the 1? Well, you get all the $500 and you get a little bit more. So there's 100% of your $500 plus 2 more percent. But we're going to take that answer times 1.02. We're going to take that answer times 1.02. And we're going to take that answer times 1.02. And this is 1 year. That's 1 year. You get it 4 times, right? So far, it's 500 times 1.02 to the 4th power. That's the same thing, right? Times, times, times. Well, what if I said, we're going to do this, I want to know how much is in there after 7 years. Well, now, if I do this 4 times a year, and it's 7 times, then it should be 500 times 1.02 to the 28. And then this NT, that's where you would get that 28 from right there. The amount of times we're compounding it times how many years this is going to happen. That's where the formula comes from. It's really not that complicated. All right, anyway, here is the formula. Christy invests $300, whoa, big spender, in an account with a 6% interest rate, making no other deposits or withdrawals. What will Christy's account balance be after 20 years if the interest is compounded semi-annually? So the amount, we're going to start out with $300. We're going to figure out, well, what percentage would you get if you compounded interest twice a year? Well, you'd get all of the money, but you'd get plus 0.06 divided by 2, because you don't get the 6% twice a year. You get, that's your annual percentage rate. So really, you're getting 3%. But then if we're doing it twice a year for 20 years, that's going to be 40 times. We'll do this, you'll multiply 40 times. So now, the calculator will do most of the work for you. 300 times 1 plus 0.06 divided by 2. And I suppose you could put 1.03 in there if you want to save a little time. And then raise to the, let's just raise it to the 40. Let's not have the calculator do all the work. We'll do a little bit of it. So we have $978.61. And we'll round to 2 decimal places since we're talking about money. But then monthly, 300 times 1 plus 0.06 over 12, 12 times 20. You can go second entry. Enter will bring up what you just did. I don't know if you know that little trick. And so now I can go over, change this to 240. Or try to. There we go. And I need this to change to, this is monthly, just 12. So I need insert, whoops, not delete. Insert 1, 2. Boom. 993. 993 and 6 cents. And then daily, we're going to go second entry, and I will let the calculator do a little work for me here. 365 times 20. And I'll go over here and change this. Delete, delete. Insert 365. 995. 94. Now, you don't get, I mean, you're going from 12 times a year to 365 times a year. Wow, that seems like you should get a lot more money. Not 93 to 95, but remember, we're taking that percentage and we're dividing by 365. So even though you're getting it 365 times a year, the percentage is so small then that it doesn't make a huge difference. But you do get more money though. Not a whole lot more. And then if you have continuous growth, which is kind of hard to imagine. We're not talking about every second. We're talking every millisecond you're getting interest. You can't come up with just a really big number and go, well, let's just make it 3 billion times a year. It's actually, there's a nice little formula for it. It's called exponential growth. And so the exponential growth is the amount in the bank account is the principal times e to the rate times time. Well, this is the formula that they would use at your bank. But a biologist is going to use N, the amount of bacteria in a petri dish, is equal to, well, how many did you start with? E to the KT. So it's the exact same formula, you guys, but a bank is going to use the P and the R, and a biologist is going to use N naught and K. So the video starts out tomorrow, or not tomorrow, but for Monday, with this formula, and it's really the same thing except a different topic. All right, so suppose this same lady is going to invest $300 at 6%. That's your constant of growth, and then times the time is 20 years. Well, we did the 365. That's sitting right here. Continuously should be more, but you're going to find out it's not a lot more. Whoops, not that. I need an E now. E to the x and natural log of x are inverse functions. That's why they're on the same key. So that's going to be to the 0.06 times 20. And so you get about $1 more. So $9.96.04.